The last speaker of this symposium is Dr. Pablo del Mazo. Pablo completed his PhD at the University of Madrid, and after a doctoral stay in Berlin, no? Yes, Berlin, and come back to Madrid at the end of the last year, and now she's currently is adjunct doctor for the moment. Okay, the title is a fashion topic now, machine learning, the electronic structure of atoms and molecules.
Mi presentación se quedó aquí, perdón.
Okay, so thank you very much for the presentation. Yeah, so in this talk, basically, I want to introduce how can we use machine learning into the solving the electronic structure of atoms and molecules. So basically, what I will try to give here is just an overview of the methods that are available right now. I am not going to give many details about any of them. I just want you to have some kind of general picture of what's the situation right now. So basically, the contents of this talk are quite simple. I will start by giving a very short introduction on machine learning. What are the ingredients we need in basically any machine learning project? And then how can we introduce neural networks into solving electronic structure calculations via variational Monte Carlo? It's electronic structure method which is already established, but how can we introduce machine learning here? And then into the density functional theory via training density functionals. So in general, the problem that machine learning tries to solve is find complex mappings between a set of inputs and outputs that we, in general, cannot write some handcrafted expression for it. So some examples of machine learning that you know for sure are, for example, the ChatGPT, which predicts the next character, words, or something given some context, stable diffusion. And more in the natural science field, maybe you know, for example, DeepMind is I think now it's Google DeepMind presented a machine learning model to basically control the magnetic field to control the plasma in a fusion reactor. And for example, you maybe also know about the protein folding problem, which yeah, people in DeepMind have also worked. So what are the ingredients to learn? Well, the first thing that you need is a model. A model is going to be basically a mathematical function, which will have, in general, many parameters in neural networks. And we can update or tune these parameters in order to acquire knowledge. That's basically to extract the information we provide from the data. Then we need to have some objective, which is going to be expressed in a mathematical function that we will usually minimize. And finally, we will need data, usually a lot of data because of a huge amount of parameters that our model has. For the training paradigms that I'm going to speak in this talk, basically, we need to know about supervised learning and unsupervised learning, which the only difference is whether or not you need output information. So in supervised learning, you will need to provide some input data and what's the expected output. In unsupervised learning, you just need to feed in the input data, and you will have some metric that doesn't depend on some known output. So for example, the most simple machine learning machinery that you can think of is basically a line. So we have a mathematical function with some parameters that we can tune. We can define an objective, which is minimizing the distance between the predictions of our model and the data we have. And we can collect data from either an experiment or whatever other source of information we have. Of course, usually in machine learning, you're not going to use a line. Nice feature in machine learning is that we use models with hundreds, millions of parameters, and then we gain a lot of flexibility to learn these features between that connect the input and the output of a data. Okay. Now going to electronic structure. So what's the fundamental problem we try to solve in electronic structure? Well, basically solving the electronic Schrodinger equation. So we have already separated our problem into a nuclear part and the electronic part, and we are left with the electronic Hamiltonian. It's just the kinetic energy of electrons and Coulomb interactions between the particles. And then we are looking for a solution of this wave function, which is usually going to be expressed as the Slater determinant of some molecular orbitals. The idea of the Slater determinant is that we need to keep the fermionic character of the wave function. Okay. Now, there's a very nice feature about solving this problem, and is that if you plug whatever wave function you want to test, for sure, the expectation value of the energy you are going to get is always going to be larger than the ground state energy. So for whatever function that you plug in to compute the expectation value of the energy, it's going to be an upper bound of the ground truth energy, the ground state energy. That's a feature that all the methods which are based in the variational principle used to solve the electronic structure. So basically, you can plug in some function, either expressed in a basis set or whatever other way you find to plug in your function, and then you tune the parameters with the objective of minimizing the energy. The variational principle basically ensures you that the lower the energy that you are predicting, the better is your wave function. Okay. So how does variational Monte Carlo solve this problem? Well, if again, we can compute the expectation value of the energy by computing this integral. Now let me introduce a new function, which is the local energy, which we can define in this way. Now, if you look at this integral, you may recognize that you can actually approach, you don't really need to solve this integral, but you can approximate it by averaging on the local energy if you sample electron positions according to your probability distribution from the wave function. So the very nice thing that variational Monte Carlo has is that it avoids the analytical integration of these complex terms, and then you are just left with an average on this local energy, which is much simpler to compute since you don't really need to go through integrals. This is why variational Monte Carlo usually has more flexibility in the ansatz you choose to solve your problem. Because since you don't have to deal with functions that depend on electron-electron distances, for example, to integrate them, then you can include much more correlation energy via terms depending on electron-electron distances without having to deal with the complex integrations on these coordinates. Then the nice feature is that if you happen to plug in the actual wave function or the actual ground state wave function, then the local energy becomes a constant. Of course, the expectation value of the energy is going to be the ground state energy, and then you have a variance of 0 in this observable. Okay, so let me show you an example of how you solve this problem with the radial part of the hydrogen hydrogen atom. So you have here the Hamiltonian, and then you propose some trial function. This is basically a textbook example. This wave function has a variational parameter A, which we can tune to minimize the energy. So how do we proceed? We propose some trial function. In this case, we have selected one value of A. We sample a set of positions, which would be these points according to this wave function. And then we compute the expectation value of the energy. For that, we compute all the local energies at each point of space, and then we can average them to get the expectation value of the energy. Now we can compute this derivative of the energy with respect to the variational parameter, and then this will guide the update of the variational parameter in order to minimize the energy. That way, we can be repeating this process to until eventually we are able to solve this problem. Okay, so now is where machine learning comes. So the nice thing again about machine learning is that we play with neural networks. These neural networks in practice have you can think of them having almost infinite flexibility. So actually, you can fit whatever function with a neural network. So why don't we use neural networks to approximate these wave functions instead of using some handcrafted ones that we think of? So that's what the two models that I'm going to present here use to solve this variational Monte Carlo problem in the machine learning scheme. Actually, you can see that both were published almost at the same time. And okay, so what's the ansatz basically that Ferminet uses? Well, it simply builds the electron wave function as the linear combination of the slated determinants of some orbitals. It is these orbitals that are substituted by neural networks. Then during the training process, basically what you're trying to do is find the neural network which is going to minimize the expectation value of the energy for these ansatz. Now, as you can see, this is actually, I mean, it works pretty well, but it doesn't have so much physics built in. And here is where Polynet actually includes much more of the physics of what we know about the electron wave function. So in particular, although the ansatz it's a bit more complex, it's able to introduce the exact Casp conditions for basically when two electrons get to the same point. Then you get what is called in variational Monte Carlo the Jastrow factor. This is just a function of the electron-electron distances. This allows you to introduce or to better describe the electron correlation much more easily than if you don't have functions that explicitly depend on the distance between electrons. And finally, we have here the slated determinant or the combination of slated determinants as we were having earlier. However, in this case, these orbitals are actually built from the Hartree-Fock solution to the problem, modified by what is called the backflow factor. Basically, this backflow factor already includes some correlation energy into the Hartree-Fock solution. And also the nice thing is that through these Hartree-Fock functions that you can get the correct exchange energy on the surface. So these are basically the models or two of the models that we can propose in this variational Monte Carlo scheme. Now, what's our objective? Well, here we were saying that the variational principle is already giving us the target of to solve a problem. Basically, we just want to find a function, a wave function that minimizes the energy. So in this case, the loss function is simply the expectation value of the local energy for the wave function that we are learning. This is the case where we are in an unsupervised learning scheme, because note that here we don't need to know how is the wave function, or we don't need to know what's the target energy. We don't really need to know anything. We just give the positions of the nuclei, sample positions for electrons, and then we just go minimizing the energy. So that's basically this part here of the data. Okay. So now let's move to the density functional theory. So in this part, I am basically going to explain how can one train density functionals. Probably of most interest the exchange correlation, although you can also try to find some others. So the central point in density functional theory is, of course, the electron density, which is just the integral over all the coordinates but one of the wave function. It's always positive, and it has to integrate to the number of electrons. Hohenberg and Kohn showed that the electron energy can be directly computed from the density via this universal functional that sadly we don't know. If we had it, we wouldn't have so much trouble to compute electron energies, which is independent of the external potential. This functional, we usually split it as a combination of things that we know how to compute or we can easily compute, which is the kinetic energy of the non-interacting kinetic energy of the electrons. It can be exactly computing constant DFT, the classical Coulomb interaction between electrons, and the exchange relation, which basically has everything that we don't know how to take into account. And here again, we have the variational principle that basically guides the search of the ground state density. So similar to what we were having for variational method, for variational methods, in this case, they're guaranteed that if you find, so you're guaranteed that for whatever density you plug into your functional, the energy is always going to be an upper bound of the ground state energy. Okay. So how do we define this functional in terms of machine learning? Well, actually, this part is still not machine learning, but in general, functional, we are going to compute it as the integral over the whole space of the energy density times the electron density. And it is precisely this term here that we are going to try to feed with some neural network, either a multilayer perceptron or maybe other methods, the Gaussian processes or whatever you want to use here. Now, what's our objective? Well, in principle, the idea would be to match the energy that our functional predicts for some reference density with the actual density, with the actual energy it should measure. Either, for example, you have computed some couple cluster energies, or you're just trying to fit it to another function. And then the data would be just a set of accurate densities and energies where you are going to train your function. So this is what Snyder and collaborators did in 2012. Actually, here they were trying to train the kinetic energy functional, because in orbital-free density functional theory, that's not known. They basically generated that data set of energies for some reference densities and trained a model on that. What they found is that they were getting accurate energies within the kcal-mol difference with the reference data, but then they tried to run a self-consistent field calculation on their functional. So with functional, you just don't want it to compute a correct energy. You also need it to be able to predict the density, or to find the density that is minimizing the energy. The thing is that when they were trying to run these SCF calculations, they were never able to converge them. Why was that? Well, basically because they have not considered that you not only need to have accurate energies, but you also need the gradient or the functional derivative of this functional with respect to the density to be smooth. This is because it's precisely this gradient which is guiding the search of the density, which minimizes the energy. So after this paper, it became very clear that you can just not train on energies, but you need to regularize your training somehow. You need to get functionals that also produce smooth derivatives. So there are I'm going to briefly talk about three ways you can regularize this kind of training. The first one, by Lee and collaborators from 2021, is to regularize with a full SCF calculation. Okay. So first, let me explain you here how I see the density functional training. So in this plot, I try to represent in blue the true universal functional that we don't know, and in red is some functional that we are trying to feed or whatever. So what we see here is that, of course, and yeah, in DFT calculations, we're always looking for this minimum in these functions. So of course, if I run a calculation on this functional, what I would get is this density as the minimum or the solution to my problem, which is far away still from the true density. So basically, what Lee and collaborators propose is to run an SCF calculation on the functional that is being trained, compute obviously this energy and this density, and then measure the distance either in energy and in density from the reference data. With that, you can update your parameters, the net parameters, in order to reduce the loss during the training. With that, you get one step closer to being able to reproduce the universal function. So if you proceed with this way, you compute or find a minimum, computing an SCF or running an SCF calculation, compute the losses, and then you would eventually reach, or your functional would eventually reproduce your reference function. So the problem with this kind of training is that we have to run one SCF calculation for each training step, what is extremely expensive. I mean, you can think of these basis sets as having probably thousands to millions of systems. So you cannot be converging these calculations for each step in your training process. That's why Patrick and collaborators also in 2021 came with a very clever idea, which is, okay, I don't want to find the minimum of my functional. What I just need to know is if this point here is already a minimum with my functional. For that, what they do is run a single SCF step from the reference density. They measure what's the change in the energy in this step, and again, you still have the reference of the difference in the energy to the true one. So with that, if you run one SCF step and you move from in the density space, then that means that your functional doesn't have a minimum there. And then you can update again the parameters of your functional to get that or to make that point closer to a minimum. Again, run an SCF step, check if there's still a change in the energy, and then you keep updating your parameters. So that's very nice because obviously it speeds up a lot the training, but then it only has a problem, and it's that in the way it's formulated, you can just train exchange correlation functionals, and which is I mean, it's probably the most interesting one. But then you in other DFT pictures, it's also interesting to train, for example, the kinetic energy one, and that's where the work I've been doing during my postdoc enters in this talk. So what I was thinking is, okay, we just want, so our problem is I need to make this point a minimum. What's the condition of, or one of the conditions of a minimum? That the gradient of the, if you want to say now, of a function at that point has to be 0. Translated to these functionals, what you have to guarantee is that the functional derivative at this point with respect to the density at this point is 0. So why don't we directly impose that? And that's basically the idea that we developed during my postdoc, and is, okay, let's add, so as regularization, let's just compute what is the gradient in this point for the reference density. If it's 0, then we are in a stationary point. Very probably we are in a minima. If it's not 0, then I have to change my function. So yeah, the training process will proceed in this way, compute the norm of the gradient computed in this way, the reference density, and then you can go updating your function. Okay. So just to give an overview of the pros and cons of the different kinds of regularization, the SCF is very slow because you have to perform a full SCF calculation for its sample point on your training set. Also, backpropagation, which is basically the algorithm by which you update the parameters of your net, presents a lot of numerical instabilities. And the nice thing is that it can be used in various DFT pictures, so consum and orbital free. For the single SCF step regularization, it's really fast and it's so simple actually that you don't really have numerical instabilities during the training, but only can be used for the consham DFT. That's just because of the way it's formulated right now. And finally, this gradient regularization basically is extremely fast and no numerical instabilities. In that sense, it's exactly the same as the one SCF step regularization, but also it can be used in any DFT picture because this gradient idea is basically the driving force in all the DFT theories for the SCF calculation. Okay, so with that, I will just go to some concluding remarks. So flexibility of neural networks finds application in electronic structure problems, either by representing the electronic wave function or a density function. Variational Monte Carlo, learning the electronic wave function in a variational Monte Carlo scheme can be performed in an unsupervised way with or guided by the variational principle, which helps in the search of the solution for the electronic Schrödinger equation. And then here we leverage the huge flexibility of neural networks, which allows encoding complex many-body correlations between electrons without relying on some finite basis sets. Regarding the density functional theory, machine learning may help find new functionals, more accurate and handcrafted ones, while you can account for physical constraints that we know about the density functionals, reducing functional and density errors. And this kind of problem has to be solved in a supervised way, account or making use of regularization techniques to smooth the derivative of the functions. And with that, thank you for your attention.
Thank you for the question. It's time for question.
Thanks for the how complex can be the how complex can be the molecule, the material you want to simulate, let's say. I mean,
so for example, for the variational Monte Carlo, I think they have gone up to benzene or something like that. So the idea is that you can get accuracies which are comparable to multi-reference CI, for example. You can really get a lot of electron correlation, reducing the number of determinants. But also, I think most of the problem now comes from having basically production codes. So right now, everything that you have is some GitHub repository that was written by some random guy, but you don't have yet some efficient codes to run these kind of calculations. But I mean, you can do that. I didn't mention because I didn't want to make it more complex than it was. But for example, you can also go to excited states with these kind of calculations. Actually, it's very simple. You just pack more of these networks, and then you just have to force them to not collapse in the same state.
I have a question about can be used constant. Can you clarify, because it's not mandatory, but it's better. Can be used.
This one?
See, this one
Yeah.
and the other one.
Yeah, so here it's just, I mean, so okay, let's very quickly, I don't know if that's obviously, so the difference between orbital free DFT and constant DFT is that the first one to approximate this kinetic energy and the exchange correlation. So basically, in orbital free, you work with just the density. In the constant picture, you actually compute the energy from a set of constant orbitals, and then you go back to the density. So what I mean when I say that can be used in one or the other picture is that in the way it's formulated, the loss function depends on the orbitals, and basically you need to have for this. So basically, this term is a matrix because you have n electrons, but in the orbital free case you just have like or you get your coefficients as a single orbital, and then the equation they propose cannot be directly used. So the idea is that in orbital free there is like no couplings between the orbitals because you just have one. And this loss term actually accounts for all the non-diagonal elements in that matrix. Okay.
More wisdom. Okay, thank you very much, Pablo.